All right, in this next video, we're going to do a little more practice with um, complex numbers in polar form, multiplications, and then raising two powers. All right, so I've got what's listed as number 51 from the Lippmann textbook here written out. So we're going to multiply these two complex numbers in polar form. All right, and I've already kind of done some of the rearrangement. We're going to multiply the radial lengths, and then we're going to multiply the e parts. So that's going to give us 3 times 2, which is 6. Now we're going to use exponent facts. So if we have the same base, which we have e, we're then going to add the exponents together. So it's going to be pi over 6 plus pi over 4 I. All right, and now when we add those exponents together, what are we going to get? So we'd have to find a common denominator. That would be 12 in this case. So we're going to have 6 as our R value, our radial length, and then we'd have e to the, we'd get 2 pi over 12 plus 3 pi over 12, so that's going to give us 5 pi over 12i, or I times 5 pi over 12. So there we go. We did it. So again, what did we do? Multiply the radial lengths, all right, and then really we're adding the angles pi over 6 and pi over 4. All right, so that's a multiplication. Let's do a division. I've got 54 copied down. All right, so if we're dividing, what do we do? When we divide numbers, all right, we got these factors here. We're going to divide kind of the factors we wish. 24 divided by 6, that's going to give us 4. All right, when we divide two expressions with the same base, we subtract the exponents. We'd have to find common denominator here, which would be 6. So that would give us, in this case, in the exponent there, multiplying top and bottom by 2, we'd have 8 pi over 6 minus 3 pi over 6 I. So then just doing the subtraction, we'd have 4 times, and then it would be e to the 5 pi over 6 I power. Again, sometimes we put the I in the front of the 5 pi over 6. So theta in this case is 5 pi over 6. So what do? Divide the radial lengths and then subtract the angles, because that's what the exponent rules and just the basic arithmetic shows us to do. We could generalize, or sorry, we're going to generalize that in a minute for multiplication and division. Now let's do it for powers. So here we've got one of the examples from above, 2 times e to the pi over 4i power. We're going to raise that to the 10th power. Now we got to remember, we're going to raise each factor to the 10th power. All right, something a little bit different happens in each case, right? When we do 2 to the 10th power, we just do that as normal. That comes out to 1024. All right, but when we raise a base to a power to another power, we know from our algebra facts that we multiply those exponents. We'd have pi over 4i times 10, or 10 over 1, which we would then simplify slightly to rewrite this as e to the I times, we'd have 10 over 4, which would be right as 5 over 2, so 5 pi over 2. All right, so that would be writing that into polar form. All right, now let's just generalize what we just did with those 3 examples, just to write this out in kind of more general form. Now keep in mind, we did it where we would have R1 times e to the I theta 1, and this other complex number would be R2 e to the I theta 2 power, and there we would multiply the lengths and then add the exponents. That's going to tell us, okay, if we're going to do it in the polar form where we're using cosine and sine, we're still going to multiply the lengths to get R1 times R2, but then we would have that times cosine of theta 1 plus theta 2 inside the cosine, and then plus I sine of theta 1 plus theta 2 inside the sine. Okay, so that would be a way to write that in terms of cosine and sine. And similar, if we're doing division, we did it in the polar form r e to the I theta above in the examples. We divided our radial lengths, so that's not going to change here. We're going to just divide our lengths of our complex numbers, our radial lengths. But then what do we do with the exponent, or the angles? We subtract the angles, all right, and then that subtraction would happen inside the cosine and then inside the sine if we wanted to write it in terms of sine and cosine in that format for the polar form. The other thing we saw in the example, I'm just going to scroll back to that, where we were taking a complex number in polar form and raising it to power was, yep, we did raise the radial length or the length of the complex number to that power, but then we multiplied the angle by that power. That fact has a special name. It's called De Moivre's theorem, and it's listed here. So again, we're raising the complex number to nth power. That results in us raising the radial length, the length of the complex number to the nth power, and then multiplying the angle by n. Okay. All right. The next thing we're going to look at is applying that slightly by kind of just doing. We could apply De Moivre's theorem, but it may be more instructive to take these steps. All right. So to compute a complex power, what we're going to use some of our algebra facts from exponent rules. We're going to convert the complex number to polar form. All right, so that would be our first step here. Then raise the complex number to the appropriate power, step 2. Use exponent rules to simplify it. And then if we need to, convert it back to rectangular form. All right, so if you're starting rectangular form, convert to polar, raise it to the power, then convert back if you need to. All right, so let's look at an example of how that's going to work out here. So I've got what's listed as number 64 plus 4i raised to the 6th power. Now, the first thing we need to do is convert that over to polar form. So I'm not going to do that in this video. We've done some of that in the previous recording. So we'd have the square root of x squared plus y squared. That'd be 4 squared plus 4 squared, which would give us 32. The angle, it turns out, if you do inverse tangent of 4 divided by 4, y over x, you'd have that angle would come out to pi over 4. So you can rewrite that as square root of 32 times e to the I pi over 4 power. Now, when we raise that to the 6th power, which we're indicated to do, now is where we've got to follow our exponent facts. So we're going to raise each factor. Right? We can only distribute exponents to factors, not terms. Then we're going to raise each one of those factors to the 6th power. So then that would be rewritten as the square root of 32 raised to the 6th power, and then we would have e to the I pi over 4 raised to the 6th power. All right, now we would do something a little bit different in each case. All right, the square root of 32 is the same as the 1/2 power, so we could think about this as 32 to the 1/2 and then raised to the 6th power. We'll multiply those exponents together, and then we'll multiply these exponents together. So we'd have I times, when we get 6 pi over 4, all right, multiplying these exponents out, 6 times 1/2 would give us 3, so we'd have 32 to the 3rd power, which we could compute, times e to the I times 3 pi over 2 power. And that's it. Now, if we wanted to, we could, well, that would be it if that's all we were asked to do. Now, if we want to convert that back to rectangular form, we should compute the power, 32 to the 3rd power, and then rewrite e to the I theta using Euler's formula. All right, I have paused the recording, wrote down Euler's formula off to the side. E to the I theta is cosine theta plus I sine theta. That's a nice way to convert that back over to rectangular form. So let's just finish this computation off here. All right, so what we've been working on is 4 plus 4i raised to the 6th power. And this can be written, again, we got 32 to the 3rd power. If you compute that with a calculator or by hand, you're going to get 32,768. Now let's apply Euler's formula. So it'd be cosine of 3 pi over 4, our angle, or sorry, 3 pi over 2, and then plus I times sine of 3 pi over 2. Okay, now just compute. All right, cosine of 3 pi over 2 is 0. That's going to wipe that out. Sine of 3 pi over 2 is -1. So what we should see in this case is that we would get negative 32,768 times I. All right, so the negative sign was thrown in the front, so that's what that comes out to. All right, converting it back to rectangular form. All right, the next thing I just want to show is if you have a TI-84 calculator, I've got an emulator brought up here. You can actually do this on a TI-84 or higher calculator. So you're just going to put 4 plus. Now, how do you do I? So we're going to do 4i. Hit second and the decimal point. I is above the decimal point. Close our parentheses off. And let's see if we did this all correctly. Looking good. All right, so we've got that same negative 32,768, and then the calculator actually shows I. So that's pretty snappy for the TI-84 calculator. Desmos actually won't do that as of yet. All right, well, let's look at one more example for this video. That's computing a square root. All right, this is not finding all of the square roots of this complex number. We're going to just compute the one square root that we're indicating here. So again, first thing, we're going to rewrite the square root as the 1/2 power. Now I'm skipping this step for this video, but we're going to rewrite -4 minus 4i in polar form. All right, and that was shown how to do that in a prior recording. So that's square root of 32. And then the angle in this case, I actually had that written wrong. It's actually 3 pi over 4. This should not be pi over 4, just only in the exponent there. That should be 3 pi over 4. All right, and then we're going to raise that to the 1/2 power. Okay, so again, what we got to do is, like we did before, distribute our exponents to each factor carefully here. So we're really going to do the square root of 32, which we could write as 32 to the 1/2 power, and then we're going to raise that to the 1/2 power. So it's a square root of a square root. And then we're going to do e to the I 3 pi over 4 power, and we're going to raise that to the 1/2 power. Okay, so we would get the square root of the square root, which we could also rewrite as the 4th root, or the 1/4 power, when we multiply our exponents there. And then we would have, in this case, e to the I times, it's going to be 3 pi over 8 power. All right, so this one doesn't come out great in terms of whole numbers like we had before in the previous example. Let's just compute this a little bit here, and then we're going to use our calculator to kind of help us rewrite that. So I'm going to leave it as 32 to the 1/4 for right now. Using Euler's formula, we could rewrite this as cosine of 3 pi over 8, and then it would be plus I times sine of 3 pi over 8. And then it's just a matter of going and doing these computations with the calculator. Okay, if we do those calculations, what we're going to end up seeing here is, all right, and I'm going to do 2 calculations at once just for simplicity here. I'm going to multiply the 32 to the 1/4 by the cosine and sine of 3 pi over 8 respectively, just for brevity for the video. If you do that, then the real part of this complex number comes out to 0.91118, rounding to 5 decimal places, and then the imaginary part is negative 2.19737i. Okay, so we could put that as plus the negative, or let's just write that as just plain subtraction. So we got that re-expressed now in rectangular form. That's it for this recording. In the next one, we're going to talk about finding the nth roots of a complex number.